Hello everyone. Today I will present monotone complexity of spanning tree polynomial revisited. This is a joint work with Arkadev Chattopadhyay, Rajit Datta and Partha Mukhopadhyay. The plan of my talk is the following. First, I will say about basic computational model. Next, I will describe two of our results, which are strongly exponential lower bound against monotone circuits and epsilon sensitive monotone lower bound. And in the end, I will talk about some open problems. An arithmetic circuit is a model for computing polynomials. There are variables labeled at the bottom layer, and these are composed by addition and multiplication gates. Finally, a polynomial is computed at the top layer. Here is an example of arithmetic circuit which is computing this polynomial. The size of the circuit is the number of gates appearing in it. A polynomial is called monotone if every coefficient appearing in this polynomial is non-negative. A circuit is called monotone if all the edge labels scalar values are non-negative. A monotone circuit naturally computes a monotone polynomial. Here is an example of monotone circuit which is computing this monotone polynomial. Some interesting examples of monotone polynomial. The first polynomial is the symmetric polynomial of degree k on n variable. And the second example is the permanent polynomial corresponding to a matrix of variable of dimension n cross n. Monotone circuits are universal for computing monotone polynomials. Say we have this monotone polynomial. A depth circuit can compute this monotone polynomial by writing it monomial by monomial. But if this monotone polynomial has exponential many monomials, then this depth circuit will be of size exponential. But monotone circuits can compute monotone polynomials in a more non-trivial way. Consider this symmetric polynomial. For k equal to n by 2, this symmetric polynomial has exponential many monomials. So depth circuit will be of size exponential size if it computes the symmetric polynomial. But the symmetric polynomial has an efficient monotone circuit. The diagram here is an algebraic branching program which is computing this symmetric polynomial. The algebraic branching program is a less stronger model than arithmetic circuit and can be converted very efficiently to a monotone circuit. On the other hand, the permanent polynomial is of n squared variables, and the lower bound for permanent polynomial is 2 to the power omega n. The known monotone upper bound for permanent polynomial is 2 to the power order n log n. We are naturally interested to understand what is the power of monotone computation, or what is the strongest possible lower bound. Here we can show. We ask this question, is there a monotone polynomial on n variables that has monotone circuit lower bound of 2 to the power omega n? This kind of lower bound we call strongly exponential lower bound. An important remark here that permanent polynomial cannot be a candidate for this kind of lower bound. The reason is permanent polynomial is on n squared variable and a monotone upper bound of 2 to the power order n log n is already known for permanent. Strongly exponential lower bound against monotone computations were known from these works. Gaskov and Sergeev in 80s, Raj in 2009, Srinivasan in 2019, Kavalar Kumar Rosman in 2020, and most recently, Hrubes in 2021. But all the polynomials that have been used in these works are in PNP, which is an algebraic analog of NP. So what about polynomials in PP, which is an algebraic analog of P? Valiant in 1979 and Jeremy-Sneed in 1982 gave us polynomial families that belongs to VP but admits exponential size lower bound. So a natural question to ask here that is it possible to get strongly exponential monotone lower bound for PP polynomials? Our work here gives an affirmative answer to this question. Our first result is the following. The spanning tree polynomial defined for a family of constant degree expander graphs on n vertices requires monotone circuit of size 2 to the power omega n. Important remark here that the number of variables in our polynomial is theta n. And this is the first strongly exponential monotone lower bound for PP polynomial. So what is spanning tree polynomial? Informally, the spanning tree polynomial for a graph has all these monomials which represent spanning tree in that graph. But we are interested in a very special kind of spanning tree. Consider this graph on 3 vertices. The spanning tree polynomial for this graph is this following polynomial. But here, every monomial is representing a spanning tree which is explicitly rooted at one vertex. Let's see how. Consider this monomial x21 times x31. The spanning tree it is representing is the following spanning tree. 2 goes to 1 and 3 goes to 1. So this is rooted at vertex 1. Similarly, the monomial x23 times x31 is representing the following spanning tree. 2 goes to 3 and 3 goes to 1. And similarly for x32 times x21. But observe, this monomial x12 times x32 is not included in our spanning tree, despite it will give you a spanning tree in the graph. Example, let's see what is the spanning tree. The spanning tree here is 1 goes to 2 and 3 goes to 2. But this is rooted at vertex 2. So that is why it is not included in our polynomial. We are interested here in checking spanning tree polynomial corresponding to a bidirected graph G on n vertices. What is a bidirected graph? A graph is called bidirected if for any two vertices I, j, if we want to give an edge between them, we need to give two edges between them, one directed from I to j, another directed from j to I. Now observe here, every spanning tree monomial is giving you a map. The map is the following. For this monomial x21 times x31, the map that we can see here is 2 goes to 1 and 3 goes to 1. Similarly, for this monomial x23 times x31, the map is 2 goes to 3 and 3 goes to 1. So the T set consists of all such maps that represent spanning tree in the graph, which is exactly rooted at 1. And the spanning tree polynomial consists of all such monomials. The upper bound for this spanning tree polynomial can be computed via determinantal computation using matrix tree theorem. This was known before. Now we will see a very interesting class of polynomial, which is called set-multilinear polynomial. Consider this matrix of variables of dimension n cross m. A set-multilinear monomial of degree n can be constructed from this matrix by picking exactly one variable from each rows of this matrix. This can be interpreted as a map from the rows of this matrix to these columns of this matrix. Say this map is pi here. And the monomial can be constructed simply in this following way. A polynomial that consists of this kind of monomial is called set-multilinear polynomial. As an example, our spanning tree polynomial is a set-multilinear polynomial. Now we are interested in proving monotone lower bound against spanning tree polynomial. So we need a structure theorem for set-multilinear monotone polynomial. This is a folklore structure theorem and has been used previously by Valiant and Jeremy and other authors. Informally, it states how to write a set-multilinear monotone polynomial into sum of simple monotone polynomials. Formally speaking, consider this variable matrix of variables of dimension n cross m and say f is a set-multilinear polynomial, monotone polynomial defined over this matrix of variables. Now, if f has a monotone circuit of size s, then f can be written as a sum of s many product polynomials alpha t times beta t, with the condition that both alpha t and beta t are monotone set-multilinear polynomial. The sets I of alpha t and I of beta t is a partition of the rows of this matrix, and this partition need not to be contiguous. Now, precisely, alpha t is a monotone set-multilinear polynomial defined over a submatrix of dimension I of size of I of alpha t times n, with this submatrix has rows corresponding to elements in I of alpha t. And similarly, beta t is a monotone set-multilinear polynomial defined over a submatrix of this matrix with the rows of that submatrix coming from the set I of beta t. This condition is saying that size of I of alpha t and size of I of beta t must be in between n by 3 and 2n by 3. This condition is called nearly balanced partition condition. Now, once we have this structure theorem, let's see a general technique to prove the lower bound. First, define a measure from the monomial state to the positive reals such that it is a sub-additive measure. And now write f as a sum of product polynomials. Now try to show that for every product polynomial, the measure is low, but for the target polynomial, the measure is large. And by showing this, we can get a lower bound on the size S. Now, using this technique, we'll prove our first lower bound result. In our case, the measure is the count of spanning tree monomials. So first write spanning tree polynomial as sum of product polynomials using the structure theorem. Now observe, any product polynomial cannot generate the non-spanning tree monomials because once they are generated, they cannot be cancelled out because this is a monotone computation. So having this idea on mind, using expander mixing lemma on a deregular expander graph, we show that there exists a constant C1 such that the spanning tree monomials, any product polynomial 80 times bt can generate at most C1 times d whole to the power n minus 1. On the other hand, using matrix tree theorem, we show that there exists a constant C2 such that the number of monomials in the spanning tree polynomial is at least C2 times d whole to the power n minus 1. Now, together these 2 points, by showing C2 greater than C1, we get our required lower bound. Now we'll go to the next part of our talk, that is our second result, which is epsilon sensitive monotone lower bound. Now we have very good lower bounds again monotone computation. So naturally we ask, can these monotone computations, can these monotone lower bounds give you a general circuit lower bound? Important to mention that in the Boolean world, this problem has an affirmative answer. Valiant gave us a special kind of monotone function which are called slice function and showed that if we can prove monotone lower bound against these slice functions, then we can get general circuit lower bound. What about the arithmetic world? Hrubes in 2020 gave an approach in this arithmetic world. The approach can be interpreted by this following problem. Is there a hard polynomial f such that for every epsilon greater than 0, this polynomial g epsilon, which is equal to e plus epsilon times f, has large monotone complexity? Here e is a polynomial which has efficient monotone circuit. Explicitly, Hrubes showed that if we pick e as 1 plus summation xi whole to the power n, which has a very efficient monotone circuit, then strong monotone lower bound on g epsilon for every sufficiently small non-negative epsilon will imply general circuit lower bound on f. Interestingly, if we want to get a general set-multilinear circuit lower bound against f, we can choose this easy polynomial as a full set-multilinear polynomial. Now, some important remarks regarding this approach. First, observe for epsilon equal to 0, the polynomial G0 has a very trivial monotone circuit. So what Hrubes' approach indicates that the hardness of polynomial f should imply that there is a significant discontinuity on the monotone lower bound of G epsilon for very small non-negative epsilons. Second important point here, that the polynomial G epsilon has monomial support full. So any support-based lower bound technique simply fails here. As an example, our previous technique where we count the number of spanning tree monomials will not work here. Informally, the reason it will not work here because there is no notion of forbidden monomials in this polynomial. So the only way is that the lower bound technique must use the coefficients very crucially. An idea here is to use techniques from communication complexity. In 2021, the first epsilon sensitive monotone lower bound against a VNP polynomial family were proven by Chattopadhyay, Datta, and Mukhopadhyay for the condition epsilon is at least 2 to the power minus omega root n. So can you show this for VP polynomial? In this work, we showed that the spanning tree polynomial for complete graph on n vertices requires spanning tree exponential size epsilon sensitive monotone lower bound in the set multilinear setting for epsilon at least 2 to the power minus omega root n. An important remark here that our lower bound technique crucially uses the discrepancy measure from the communication complexity model. So what is the communication version of spanning tree polynomial. Let's see what is the spanning tree communication problem. The problem is the following. A fixed vertex set V has been partitioned in between Alice and Bob, and Alice gets VA and Bob gets VB. The input to this problem is a set of edge maps. What is that? So Alice gets all the edge deduction on her part of vertices, and Bob gets all the edge deduction in his set of vertices. And together they want to check whether these two sets of edges forming a spanning tree rooted at vertex 1 or not. The vertex 1 is a fixed vertex in our given vertex set V. For first, we showed that this problem is very hard under a fixed partition of the vertices. And we showed this by giving a gadget reduction from this inner product problem. The inner product problem, which is a very hard problem, is defined over two sets of variable x and y. It is a Boolean function, and it computes summation I equal to 1 to n xi times yi mod 2. We show that for an input instance x comma y, if ip of xy equal to 1, then our gadget graph gxy has a spanning tree. And if ip of xy equal to 0, then the gadget graph will have a cycle. Let's see what is the reduction here. We show the reduction for a 2n-bit inner product problem. Our gadget reduction has n plus 1 many gadgets. For I equal to 1 to n, I will define the ith gadget. And later I will define the n plus 1th gadget. The ith gadget has two Alice nodes, one in the top, one in the bottom. And two Bob's nodes, one in the top, one in the bottom. Depending on the values of xi equal to 0 or 1, the Alice nodes are connected either to the Bob's nodes on the same gadget or connected to the Alice node in the next gadget. Let's see how they are connected. For xi equal to 0, the top Alice node in the ith gadget is connected to the top Alice node of I plus 1th gadget. Similarly, the bottom Alice node of ith gadget is connected to the bottom Alice node of I plus 1th gadget. For xi equal to 1, the top Alice node of ith gadget is connected to the top Bob node of ith gadget. And for xi, similarly, the bottom Alice node of ith gadget is connected to the bottom Bob's node of ith gadget. Now see how the edge direction is going out of the Bob's node, depending on the values of yi's. For yi equal to 0, the top Bob's node of ith gadget is connected to the top Alice node of I plus 1th gadget. Similarly, the top Bob's node, the bottom Bob's node of Alice's the bottom Bob's node of ith gadget is connected to the bottom Alice node of I plus 1th gadget. And for yi equal to 1, the bottom Bob's node of ith gadget is connected to the top Alice node of I plus 1th gadget via this edge. And similarly, the top Bob's node of ith gadget is connected to the bottom Alice node of I plus 1th gadget via this edge. Now let's see what is the n plus 1th gadget. The n plus 1th gadget has one Alice node, that is one Alice node, one Bob's node. The Bob's node is connected to the root R, and that Alice node is connected to the first gadget top Alice node. Now observe what is happening here. For the value xi times yi equal to 0, there are two cases can happen. For xi equal to 0, the Alice node, the top Alice node is connected to the top Alice node of I plus 1th gadget. Similarly, the bottom Alice node is connected to the bottom Alice node of I plus 1th gadget. But when xi equal to 1 but yi equal to 0, there is a path from top Alice node of ith gadget to the top Alice node of I plus 1th gadget via this vertex bi1. Similarly, there is a path from bottom Alice node of ith gadget to the bottom Alice node of I plus 1th gadget via this vertex bi2. But interesting thing happens when xi times yi equal to 1. Observe, there is a path from top Alice node of ith gadget to the bottom Alice node of I plus 1th gadget. So there is a change of layer here. Similarly, the bottom Alice node of ith gadget is connected to the top Alice node of I plus 1th gadget. Now for xi times y equal to 1, this changing of layer in the paths will help us to show how this reduction works. So let's see, let's get an example. Consider one instance of the inner product IP. If we use a 3-bit inner product and the values are xi are all 1 here and yi's are all 1 here. These are all the vertices of Alice and Bob in my gadgets. Let's see what happens to a path that starts from A11. So there are three i's such that xi times yi equal to 1. And 3 times the path that starts from A11 will change its layer. And if it changes layer odd many times, observe it will eventually reach the B41 vertex. That is the n+1th gadget Bob's vertex. So once this path reaches this B41 vertex, it can go back to the root, it can go to the root R simply. And observe any other vertex that is not on this path, there will always exist a path from that vertex to either this B41 vertex or this A41 vertex. If it has a path to this B41 vertex, then it will already connected to the root. It is already connected to the root. But if it has a path to the A41 vertex, then it is connected to this A11 node via this back edge. And we already have seen that there is a path from A11 to root. So whenever there are odd many i's such that xi times yi equal to 1, there is always a spanning tree is forming in this gadget graph. Let's see the 0 instance of IP. Consider this instance where x1 equal to 0, x2, x3 are 1, and y1, y2, y3 are all 1. So these are the vertices of Alice and Bob in the gadget. And just look what is the yellow edge is going here. How is the yellow edges is going here? Intuitively, the path that starts from A11, since there are even many i's such that xi times y equal to 1, will change the layer even many times. And always eventually it will reach this node A41. Generally, the top Alice node in n+1th gadget. And once it reaches here, it will always complete the cycle via this back edge. So whenever we'll get a 0 instance, that is there are even many i's such that xi times y equal to 1, the path that starts from A11 will change its layer even number of times, and it will complete the cycle by reaching this top in Alice vertex of n+1th gadget, and by using this package. So this completes the reduction, and what we saw that if our inner product instance is 1, then our gadget graph has a spanning tree. If our inner product instance is 0, then the gadget graph will have a cycle. Now we'll come to a very important measure, which is called discrepancy measure for the communication problem. Say we have a communication problem, and this is a communication matrix of this communication problem F. The communication matrix has rows corresponding to every input of Alice and columns corresponding to every input of Bob. For an Alice input X and an Bob's input Y, the entry XY is simply the value of f of x comma y. So it is a Boolean matrix. Now, a rectangle of this matrix is a submatrix of this matrix such that the rows and the columns of this submatrix may not be contiguous in the original matrix. So this is a rectangle's example, and as I mentioned with different color, this is all the entries are 0 here. So this is 0 monochromatic rectangle we say. And similarly, this is a 1 monochromatic rectangle, but this is a mixed rectangle. Informally, for a rectangle, the discrepancy measures how much the rectangle is mixed. Formally, the discrepancy comes with a distribution over the inputs of these matrices, over the entries of these matrices. And given this distribution for a rectangle, the discrepancy measures the absolute weighted difference between the zeros and ones of that rectangle. Now, the discrepancy of this whole matrix is the maximum discrepancy of the rectangle that is appearing in this communication matrix. And the discrepancy of this communication matrix under this distribution delta here is the discrepancy of this function communication problem f. Now, intuitively, if the more the rectangles are mixed, the harder it is for a low-cost communication protocol to distinguish the zeros and ones in this matrix. So the lower the discrepancy, the harder the problem becomes. Shore and Goldrich in 1988 showed under uniform distribution, the inner product problem has discrepancy at most 2 to the power minus omega n by 2, where size of x and size of y are n. Now, immediately by our reduction, what we get here is that for a fixed partition of vertices on the set for the fixed partition of vertices, there exists a distribution such that the spanning tree problem has low discrepancy. So we get the low discrepancy of spanning tree polynomial for a fixed partition. But are we done here? No. The reason comes from the structure theorem. Observe, using structure theorem, we can write the spanning tree polynomial as a sum of product polynomials. Now, every product polynomial works like a rectangle, where rows of the rectangle comes from all the monomials of alpha t, which belongs to Alice, and columns of this rectangle will come from all the monomials of beta t, which belongs to Bob. And similarly, they get an I of alpha t and I of beta t, which is a partition of this n set. Now, for different product polynomial, the partition may be different. That is why if the partition is changing, then in order to get the discrepancy low, we need to change the distribution also. But this is a local measure. What we need for the lower bound is a global measure. And that we get in the following way, via uniform distribution. We essentially got a universal distribution under which for every nearly balanced partition, the discrepancy of spanning tree volume remains low. And once we have this distribution, we are able to transfer this discrepancy bound to the lower bound using a very novel correspondence theorem. Our universal distribution intuitively is the following. We pick the gadget graph gxy uniformly and then embed it in a bigger graph after permuting the vertices of the bigger graph randomly. Now, by using this uniform distribution, we are able to show that the spanning tree volume has discrepancy remain low. The Discrepancy-Sensitivity Correspondence Theorem. The theorem states the following. Consider any 0-1 set-multilinear polynomial f. The 0-1 means the coefficient of this polynomial is either 0 or 1. Now consider the natural communication problem CFP with respect to this polynomial f. As an example, recall for spanning tree polynomial, we introduce this communication problem spanning tree. Now, if you have a universal distribution delta, and if you can show that the communication problem CFP has discrepancy at most gamma with respect to delta for every nearly balanced partition P, then the monotone complexity of fn, m minus epsilon times f is at least epsilon by 3 gamma as long as epsilon greater than equal to 6 gamma by 1 minus 3 gamma. The polynomial fn, m is that easy set-multilinear polynomial. That is the full set-multilinear polynomial that we have already described before. What it states here simply that if we have a discrepancy upper bound like 2 to the power minus omega n, then for epsilon at least 2 to the power minus omega root n, we can get an exponential size lower bound. And that is what we exactly got here. We construct an universal distribution delta such that the discrepancy of spanning tree problem with respect to delta for every nearly balanced partition is at most 2 to the power minus omega n. Now let me summarize our whole work. we showed the first strongly exponential separation between monotone VP and VP. We gave the first exponential size epsilon sensitive lower bound against a VP polynomial. Now, some open problems. Find a polynomial with polynomial size non-monotone formula but has strongly exponential size monotone circuit complexity. Remember, our spanning tree polynomial that has been used in the monotone VP versus VP separation has an efficient ABP because of determinantal computation. We still do not know if it has any non-monotone efficient formula. The second problem is give a strongly exponential size epsilon sensitive lower bound. The reason is our target polynomial in that epsilon sensitive lower bound problem was the spanning tree polynomial for the complete graph on n vertices, which is of variable n squared, and the lower bound is 2 to the power omega n. We have more interesting open problems. For that, we invite you to check our paper using this following link. Thank you.